Good morning, dear students. So in the last few classes, we were discussing about the hydrogen spectra, then orbital angular momentum, spin angular momentum, and today we will go a little bit deep into hydrogen spectra. How spin orbit, today we are mainly looking into how spin orbit interaction leads to fine structure of hydrogen spectra. So hope you are following the classes. If you have any doubts, please feel free to ask me either through WhatsApp or in the comment section, or you can make a call, and then I'll clear the doubts. So let us go into the class. So today we will mainly look into hydrogen atom spectrum. So in the first few classes we have seen the various spectral lines, Lyman series, Balmer series and Paschen series. Now today we will see how the spin orbit interaction is going to modify the spectral series of hydrogen. So basically the spin orbit interaction Hamiltonian, this is given by 1 by 2 m square c square 1 by r into dv by dr into L dot s. So you need to study only the final result. For an electron in a hydrogenic atom, VR is nothing but the potential energy, that is minus Z square by 4 pi epsilon 0 into R. And again the final expression, this will give from the spin orbit Hamiltonian, you will get the energy values, interaction energy value, that depends on J value, L value and S value. Now here in this notation, the R is the Rydberg constant and alpha stands for the fine structure constant, and Z is the atomic number. Now if you remember in the first class, in the hydrogen spectrum corresponding to n is equal to 1, L is equal to 1, you have minus, the energy was minus 13.6 and only one state was there. N equal to 2, you have L equal to 0, 1, two states were there, and we have assumed that these two states were degenerate, that means these two states are having the same energy. Now what happens due to spin orbit interaction is that this degeneracy is removed. So this happens in the case of L equal to 1, L equal to 2, L equal to 3, etc. But L equal to 0, the spin or the Hamiltonian, that means spin orbit interaction Hamiltonian is 0, so it will not be having any effect. But if L is more than 0, L is equal to 1 or L is equal to 2, you will be having two states, and these two states, for example, J is equal to L minus half and J is equal to L plus half, these two states will be having different energies, or their degeneracy is removed through spin orbit interaction. So let us take the example of a p electron. P electron case, in that case L is equal to 1, S is equal to half. Now the possible J values are 3 by 2 and half. So the total angular momentum, this is the total angular momentum quantum number J, and this is the total angular momentum vector, that is root of J into J plus 1 units. That means J into J plus 1 into H cross, and H cross that is usually taken as J into J, root of J into J plus 1 units. Now when J is equal to 3 by 2, it gives you a value of root of 15 by 2, and when J is equal to half, it gives you a value root 3 by 2. In the first case, what happens, L and S reinforce. Reinforce means L and S are in the same direction, and physically speaking L and S are in the same direction. And in the second case, L and S oppose each other. So thus the total angular momentum is different in magnitude in the two cases, and hence what happens, since the moment is different, the energy states, instead of a single energy state, there will be two different energy state. So usually the spin orbit interaction is more prominent in heavy elements, as the spin orbit interaction energy is proportional to Z raised to 4. Z is the atomic number. So once the atomic number is more, obviously the spin orbit interaction will be, energy will be more. So in the case of hydrogen, its effect is less, whereas in case of atoms, heavier atoms, its effect is more. Again, the separation between the doublets decreases as L increases. That means the separation between P and D is more compared to D and F. Like that it goes. So when you define the fine structure of hydrogen, you can define it as the hydrogen spectrum including the doublet level. But earlier what we have seen, the Lyman series, Balmer series, Paschen series, all these are there will not be any doublet structure. That is simply the hydrogen spectra. Now fine structure of hydrogen will be having the doublet levels. So we can have a look at these spectral lines. The same spectral series, 1s, n is equal to 1s, and here you have the energy. So here it is minus 13.6, and this is the 2s state, that is also a singlet state. And look at the 2p state. Earlier it was having a single state, but now due to spin orbit interaction, this state is split up into two. One is an upper level which is having a value of 3 by 2, j is equal to 3 by 2, lower level which is having j is equal to 1 by 2. Now 3s, you have to consider 3s again, L equal to 0, there will not be any additional states, but 3p is split into 2, 3 by 2 and half, 3d again 5 by 2, 3 by 2. So like that it goes. Now for the spectral transition, what we have, the spectral transition is based on the selection rule. In the previous class we have seen the selection rule as delta n can have any value, delta L is plus or minus 1 only. Now we have to include the selection rule for j also, that is delta j is equal to 0 or plus or minus 1. That is the selection rule. Quantum mechanically, this indicates the possible transition between various states. Now as per the selection rule, now what I have shown is the spectral transition between 1s and 2p state. So you can have 1s 2p, 2 transition. That means the spectral line is split up into 2 instead of a single line. Earlier we have shown it as a single line, now we have 2. This is actually doublets. Now again 1s, this 3p transition is possible, then that is also a doublet, that is shown in the figure. So the 1s 2p and 1s 3p transitions are shown in figure. If spin orbit interaction was not considered, the transition 1s 2p is a single line. When spin orbit interaction is included, it splits into 2 lines. I hope it is clear now. Now similar is the situation for other transition. The same thing holds for other transition also. The transition involving 2p and 3d levels gives 3 lines instead of 2 lines. So you can have the transition here p half and p 3 by 2. So p half, p 3 by 2 to d 3 by 2 transition is possible. From 3 by 2 to 5 by 2 transition is also possible. And from 1 by 2 to 3 by 2 transition is possible. But from 2p 1 by 2 to 2d 5 by 2 transition is not possible, because here delta j is equal to plus 2. As per the selection rule, delta j should be either 0 or plus or minus 1. Here 2 actually indicates the doublet. So because corresponding to s is equal to half, you will be having 2 lines. So that is actually known as the multiplicity, that we will see in detail in the next class. So thus the inclusion of spin orbit coupling increases the complexity of hydrogen. So from the normal spectrum we have gone a little bit deep, that is to the fine structure of hydrogen spectrum. Thank you.